Hello. Recently, I had the fortune to interview Sanjay from E3D about the E3D Revo, their new hotend. Now, this interview was over an hour long, and we touched on things such as how it's manufactured, some of the design aspects of it, and why certain things are the way they are. Now, this interview is going to be broken up into several parts and be edited around just for sake of consistency and to please the YouTube algorithm gods. So in the first part here, we're going to be talking about the Revo's heater and what makes it special. So let's get started.
This is Sanjay. For everyone who doesn't know who Sanjay is, can you give me a quick background on what you do and who you are?
Yeah, my name is Sanjay. I'm a nozzle narcissist, I guess. I really like nozzles. I helped found one of the founders and directors of a company called E3D. And we make extrusion systems for 3D printers.
Yeah, so we'll try and cover a few things, but we are time limited. So we'll start with the heater itself, because you've released plenty of information so far on the Revo. And for those who haven't, read the blog post. There's videos on it already. There is content out there already for those generalized about it. But a lot of questions have popped up about the heater, because you now have this all-in-one circular heater that surrounds the nozzle brake, although it's the Revo nozzle now. I believe that's the correct term. But a lot of people are comparing it to, there already are circular heaters on the market. The MaxiWatt, for example, that's been around for a few years. So if you can give me a quick breakdown of what current heaters, the existing heater cartridge we're all used to, how those are made and how those work, and then compare that to what you've done different with Revo.
I wonder how quickly I can do this. Okay, so a heater cartridge, you get a nichrome wire, it's a nickel chromium alloy, and you wind it around a little matchstick, kind of like this iPad pencil. You wind it around, so you have this thing, it's called a mandrel, and then you take a piece of metal tube, and let's
Need props. We need props.
So you've got this thing that's now wound with wire, and the wire, it's actually got a hole straight up the middle that you pass one of the wires up, and then you take it and you put it inside a metal tube, and you hold it kind of in the middle, and whatever you do, you don't want it to touch the sides, because this is the glass is steel, and that will short and conduct the electricity. So you hold it in the middle, and then you kind of pour magnesium oxide around and pack it into place. So magnesium oxide is just a powder, and it's a ceramic that's fairly thermally conductive, but it's also very soft, kind of like chalky and talcum powder-like. And so then you take this whole little assembly with the wires and stuff, and you might weld some lead wires on at this point, but you get the idea. You got this thing. And then it goes into a big machine that basically crushes it. And that it goes, you might start with an 8 or 10 millimeter heater, or 10 millimeter tube, and then crush that. And that compacts the magnesium oxide ceramic around the coil. But that compacting is quite a chaotic process. And it stretches the wires and the joints, and everything's deforming. I mean, you're just like, there's entropy everywhere. You're just like crushing
It's hard to keep it within a certain spec, I guess.
Yeah, I mean, if you ever looked at heater cartridges, a lot of the cheaper ones on the ends, they're kind of tapered in, because it's fed into a machine with rotating hammers around the outside that kind of like like this, and you feed it in, and it squishes the whole thing around. But yeah, the tip gets squished more than the back, so you end up with this. To combat that at E3D, we then centerless grind the heater cartridge afterwards to bring it back into like a well-specified circularity tolerance. It's kind of surface finish and cylindricity.
Yeah, because you could see that. I've seen that like on high quality cartridges. They got the ground finish, and then you go buy the cheap 5 cents each pack for 20 off AliExpress, and they're all just mangled steel essentially in the shape of a tube.
Yeah, and they're quite pitted, and you can see but
the internals is pretty much the same across the board, right? The internal, how it functions, is pretty much the same from every manufacturer.
Precisely so. Manufacturing process. I mean, there's actually just kind of one company that sells all the machines to build it, and all the mandrels and the classic Chinese industry. It's all kind of interconnected. Moving onwards, the MaxiWatt heater. The maxi-watt heater is a heater cartridge, bit longer, bit thinner, and then you bend it into a circle and you push it into a metallic housing. I think theirs is copper with nickel plating. Well, no, it's aluminium. It's aluminium, then it's welded shut with a plate-like construction.
Okay.
And cables get added on and so on and so forth.
So now for the Revo heater. So what's the Revo heater? How is that different?
Yeah, so we don't rely on nichrome wire. We start with something a bit like this. Very thin-walled alumina ceramic, which is a highly thermally conductive ceramic. It's not dissimilar to what you might make a ceramic knife out of. It's like that kind of grade of engineering ceramic. I check myself on that, but you take this and then we print on the outside, and it's kind of like silk screening. It's a process where it's a screen print, right? So, but instead of screen printing like white ink onto a PCB, we screen print a tungsten, a paste, essentially, a tungsten ink around the outside through a kind of stencil. And that stencil is made with a photolithography etching technology. So it's very cheap and easy to make yourself a new track. And so you can like rearrange the heat and the size of the tracks, their thickness, their concentration and where they are. So you can literally paint heat onto the
so you have so much more control over it.
Right. And so if I want to put like 50% of the heat here in the bottom third, and then the rest of it up here, you can do that. Or you want to put it all on the left and a bit on the, you can do that. And then again, it's kind of like PCB tech in that we then put a layer over the top, but with vias in it essentially. So there's another layer, a capping layer, that is, again, it's a ceramic, so that you protect the printed ink, but it has little holes in it that are like windows to the crack, and then we braze, kind of like soldering, just a higher temperature version of soldering. We braze wires to it, and so you end up left with something like this, that has wires brazed to the side, and this beautiful printed track. So if you get a Revo and look really closely at the sides, you can actually see that grey trace winding its way around, like a serpentine trace. And if you get one of these before it's turned into a final Revo heater and you shine a light down here, it's all translucent because it's like after you lay it up, all these inks and such, it goes back in for another sintering process. Right? Forgot to mention that, but what that does is it means that the cap layer and the ink, it all kind of sinters together, essentially melts together. And so instead of having an assembly that's made of crushed up together powder, you now have a solid state system. Like it's a fully bonded solid state integrated heater circuit.
Nice.
And
so
instead
you should
of it being
everyone should be pretty much exactly the same. You shouldn't be seeing any variances. They should all be pretty much like identical now going forward, correct?
The variance is about the same compared to or the standard deviation from the mean is the same, but the mean is always in the middle.
Okay, I see what you mean.
Whereas if you get a batch of heaters, sometimes they are like shifted up and down because the machine that was pulling out the nichrome was pulling out a bit more that day. It's really getting into the weeds here, but the really, really cool thing is that these heaters, a solid state heater, that there's real deep magic, and you're printing it around the circle. It's kind of like how you screen print on mugs and stuff. It's similar to that.
Okay.
I won't go into too much detail, but it's freaking cool. Now, these are positive temperature coefficient heaters, which is a fairly new thing in the world of 3D printers. definitely not new to anyone that does any kind of electronic heating system. What this means is, as the heater gets hotter, its actual power output drops off. So when you reach around 350, it's dropped down to maybe about 15 watts. So you go from 40 watts at 20 degrees centigrade to something like 50. Don't quote me on those numbers, but it's significantly
as it gets hotter, it
the,
draws less power, basically.
Yeah. And this isn't like a controller that's built in. This is fundamental to the materials. It's as the atoms and the tungsten particles and the ceramic expand, there's less conductivity inherently in the material. So this is a really incredible safety feature, because you're not relying on a thermal fuse, you're not relying on an algorithm. And don't get me wrong, we've got some amazing algorithms that really look after your heater incredibly well, and know how it should be behaving, and if there's any deviation from that. All of that still works with these systems. I think there could be some optimizations to be had, but all of that still works. What we're adding is a fundamental to the material, deep, inherent safety, which means that, you cannot melt these things down.
Wow. So let's give you a scenario here. Okay, I built my printer. I bought a Revo. I got a 24-volt Revo, 24-volt power supply. But I was cheap and I used an ANET board. And I just went and had my MOSFET blow, and now it's getting fed 24 volts all on. It's a MOSFET fault, so thermal runaway isn't going to protect me. Yep. So how hot is it going to get?
I wouldn't like to quote a number, but what I will tell you is it will not melt down.
Yes.
So it is, I'm not going to say impossible, never say never, but I have tried to melt them down using all of the power supply and all of the voltage into the lowest voltage heater, and all I can get is the most extreme of extreme errors. So your MOSFET blows, you installed a 12-volt heater in a 32-volt system, and it blows open, and your power supply is just able to dump in the current. It doesn't melt down. It just sits there. It'll glow a little bit in that very, very extreme situation, but it doesn't melt down. It doesn't drip molten aluminium or pop a nozzle that is over the flash point ignition temperature of PLA down into your print. And that's the scary bad failure mode. You don't want that. Nobody likes that. So that failure mode with Revo is orders of magnitude less likely to happen. I'm going to say impossible. But
extra safety is always good. Extra safety is always good, and it doesn't cost you anything extra. It's drop in and it's solid state built into it. You don't need any firmware. You don't need any chips or anything. Right. It just does it.
Yeah, and this really helps for things like UL and CE certification and the like, where you can't just have two algorithms running on one processor and say that I now have two redundant safety systems. They would class that as one. So oftentimes you need two redundant in order for them to be accepted as compliant devices. You need that. So on heaters, on things that get hot. So that's
Okay. Now you said it was a 40-watt heater. Was that kind of just what it ended up with the form factor you had and how you were designing the heater itself, or were you aiming for a 40-watt heater? Because I know it's what a lot of people call a standard flow heater, and people want that high flow. So is there the ability to go bigger or smaller, or you're kind of limited by your size and form factor for the heater size?
Oh, the great thing about this process is it's software definable. So if we wanted to make a longer one and print more track and add more power, we can go wild, right? You want a 16-volt, 44-watt heater? Sure, we'll print you one of those. No drama. Which is cool. That's fun. But we started with 30-volt. 30 watts. Ooh, pardon me. Because of the inherent safety, we were able to just add a bit more power on, and there was still bags of headroom left within the safety margin and the PTC effect. So, yeah, let's throw some more power in, because the beautiful thing is that it means that you can add more power at the times when you need more power, and tune the PTC curve such that you get less power when you really don't want it. And so, like, it's a really neat little bit of like designer materials almost. Yeah, and then moving onwards, I guess so we've got this little ceramic heatery thing with all of its glory inside, and people have done similar metal ceramic heaters before. So, credit where credit is due. Like the Delta Printer guys put theirs on a hotend. And I think there's another one that I don't recall. But we're not the first to use a metal ceramic heater. What I think we are the first to do, though, is to take that and integrate it into a system that is a truly fully capable all-metal hotend system. So previous metal ceramic heater-based 3D printer heaters, they would bond the heater to the nozzle with something like a high temperature epoxy or silicone adhesive. So essentially, it's an organic molecule, right? And organic molecules don't do well above 250 to 300 degrees centigrade. That's just a kind of fundamental limit of the carbon-carbon bond breaking point. So we knew right from the start we had to bond the heater to this metal thing, and that turned out to be one of the most significant challenges, actually, because we take our heater and we pop it over something that we call the mandrel, which is a turned metal part.
Now, what material is the heater block made out of? It's a brass copper, right?
Yes.
Okay, so aluminum's gone.
This is a real. Aluminium's out. It's a copper alloy.
Okay.
I mean, it's over 95% copper, I believe. I guess majority copper. I'm gonna shut my mouth because that's a really big deal. Anyway, that's really cool. It's really, really cool. Yeah, that one really gets me. That really gets my juices going.
Metallurgy, yes.
Yeah. I mean, right to the point where we're considering doing a custom run and tweaking. So, and this is where we're getting really freaking cool. Now, you have your heatery thing. This that we talked about, this PTC, but it's a very thin ring. It's like a 0.5 millimeter thin ring, and you can almost see through it. It's kind of translucent. And you drop it onto this metal part that's been produced on this bar-fed process, printed thing that's sintered solid state onto bar-fed little round widget. But now you have a gap between the center, so this is your ring going on, and you've got a gap between the heater and the thing in the middle. We cut some channels and stuff into the side of the top hat, which is where the wires and the thermistor kind of sneak up, and a few other features. There's a little ridge that allows us what we call the strain relief, which is that sheet metal part that gets clipped onto the top at the end. You take that and you sneak a thermistor in down the side into a special channel, and the head of the thermistor has a tiny little pocket where it kind of nuzzles in and gets all into place, and the strain relief is in place. And then we have this again. This is again another real nice bit of designer materials. Is this adhesive that we took some existing recipes that a ceramic adhesive company had, and we modified them so that the process was faster, and that the adhesive itself was more thermally conductive. Again, just really, really neat, real nitty gritty. And so that's a kind of a cement, and it gets kind of injected into the gap. So you kind of inject it into that gap, and it then fully wets out and fills that void in the middle. And it's the interfacial layer between the heater and the thing that you kind of want to heat in this case, which is that mandrel that you want to get hot. There's a whole curing cycle and process, and what you end up with is the heater being completely bonded. It's not like they're just in contact. They are one piece now. That heater is now a single, fully bonded object.
Yeah, it's not coming apart.
With a hammer, maybe, it'll come apart. I mean, I've taken my fair share of them apart. It just,
under normal operations, it's not coming apart.
Under normal operating conditions, no, it's not coming apart. And that is actually one of the other big features. Is I'm sure many of the people, if you've gotten this far into the video, listening to me ramble on about this, you've almost certainly broken some thermistor wires. Like,
yep.
If you stayed long enough for this, you've been playing this game long enough that you've broken some thermistor wires. We've all been there. Thermistors are delicate, and these wires are all kind of small, and everything is small. Everything is so small. It's a real pain. But one of the really cool things we've done is this strain relief thing on the top. So clipped onto the central core, the solid metal core, is the sheet metal part, and the wires for both the heater and the thermistor come up, and then they get this thing has wings, kind of like a crimp connector that you crimp on a Molex or DuPont header. We actually kind of took that and looked at it and did that scaled up a bit, and it grabs all of those cables together into a single bundle, and we crimp that around it, and so it's holding on to all of those wires for you, so you can't like pull the thermistor and rip its legs out of it. So.
That's already saved me once. That thing has already saved me once.
This is really important because 3D printers move, and wires and moving gets very difficult very quickly. So we needed a system that didn't allow the wires. If you've done a mediocre job of strain relieving the system yourself, it has a lot more resilience in terms of cable strain and flexion and fatigue than any of the systems that we've seen in the past. So the robustness level is through the roof. Because I often hear and see people say, so if the thermistor legs break, then I'll have to replace the whole Revo heater. Yes, that is technically correct, but also we fixed the problem of the thermistor legs breaking, which is the real fundamental underlying issue, by fully integrating it and providing this like steel armored cable strain relief exit system.
It does flex a bit, because I've had people ask me about it. It does. You can bend it if you need to, like if your tool head needs the wires to be coming at an angle. Don't do it often though, but it can bend if you need to.
Right. So it's malleable. It's not a spring steel. It's not a hard steel. As with any kind of crimp connector thing, it needs to have an amount of softness so you can squeeze it into place and have that kind of bite and cinch down onto the cables. And so, yeah, that exit wire thing, it has an amount of, you can take it and bend it into the right kind of shape-ish within certain limits to suit where the wires have to go in your printer. But afterwards, it is a rigid body in effect. It is not designed to allow accessions, but it is, you can kind of get the wires to go and exit as you please. Once we've built this entire heater, it then goes on to a quality control rig. And a quality control rig doesn't just measure the resistance of the things and say, is this good? We run it exactly like it will be run by you and your printer. So we take that heater, and we connect it up to a system that heats it up and ramps it up hard all the way up to its maximum temperature, turns on fans, blast cools it, rinse and repeat a whole bunch of times, temperature holding. And this whole curve, we know what it should look like when we do all of these like things, and we measure data along the way, capture all of that. We know how a heater should be behaving when correctly and operating correctly. And we test it like you will use it. So we put it through the same set of challenges, as it were. Train like you fight, fight like you train. And so the quality control rig, it works like that. And all of that data, just like Prusament, like we're gonna put our money where our mouth is, and so you will be able to go and all of this data is serialized. Every single heater is serialized as they're going through all of the manufacturing steps and processes. It's really freaking cool. There's lots of QR codes and barcode scanners along the way for every single little process. The kind of the crimping, the bonding. We're capturing data about all of these things all along the way. And then finally, at the end, we capture a whole bunch of data about how this heater is performing and behaving across the whole range of temperatures that it's expected to encounter in the course of its use. And that is really freaking cool, because it's one thing to quality control some spec numbers. It's a completely different thing to actually observe the system in operation and verify that its operation is within bounds of what you are going to do. So this isn't quality control by inference. This is quality control by observation of the true performance of the system. And then we're going to put that on public, so you can go and scan your hotend, put its serial number into some kind of web UI, and the graphs.
So will you be able to pull up like, okay, so this is like the PID values for the heater. Would that be something that would be on there?
We're considering trying to add that, but at the moment, individual PID auto tune would add a lot of cycle time.
Yeah, good point.
But it may be that we're able to build a system that infers and calculates what the PID set point is and should be. But frankly, when we're running the machine, we just use one set of PID values and everything is totally fine. And PID tuning these things is a piece of piss anyway. It's just it's so ridiculously easy to control them.
Yes, that's one thing. Like they're so, like, obviously I only have the one beta unit, but it's so consistent for like the heat up times, its stability and everything. Yeah, they're just like dead nuts on the whole time, and that's because the thermal mass and lag of the system, like where the atoms that are generating heat are and where the atoms that are in the plastic and flowing and taking away that heat, that distance and the amount of like travel and lag between that has just been reduced massively, and we're getting the sensor like right in next to where it needs to measure. And so we've taken a system that was kind of really quite large and bulky and aluminium-y in this whole block, and you had the heater over here and sensor. We've crushed that down by something like 5x is the increase in not heat up rate, but the responsiveness. And those are very different things. But when you look at your graph, if you like request, a ramp to 250, you ramp up really fast to 250, but you don't get that like overshoot
over the. It just goes whoop, and then.
Yep, that is one of the things I've noticed. Is if you got like a Dragon High Flow or some other big blocked heater or hot end, and you have like a 50-watt cartridge in there, it always overshoots quite a bit.
Yeah, you get that boing, and that's because those systems, in control theory, we would call that dead time. And dead time kills control loops. Dead time is just the enemy of it. Like dead time is like backlash in a gear set, right? So this is like the thermal equivalent to backlash. Like we basically the kind of amount that when you stop adding input in and then try and go in the opposite direction, you end up freewheeling. You turn off the heat and you don't actually get any reaction until the heat has traveled through the system and stopped traveling through the system. And the actual impact of your change in input doesn't translate. It's like we've gotten rid of the thermal backlash, as it were.
Okay, and this is all in-house too, right? Like everything for this new heater, this is all in-house.
Yeah, from the bar, the actual heating element printing and sintering process, that is not done in-house. That is subcon. But everything after that, including the machining at the moment, we're machining them all in-house right now. This has been the biggest challenge that in terms of things that we've developed at E3D. This has been the biggest challenge to date by far. It's like a Revo heater is just a cylindrical heater around another cylindrical part. You can go on CAD and draw one of those up, and it seems like lots of renders of Revo alike heaters have suddenly started to pop up from other folks. So like, it's very, very easy to take a round heating element and draw it around a thing and then make a prototype. Producing 1,000 of those a day and building the machinery to produce 1,000 of those a day, that is a different problem entirely. And that is what we've been solving over the last couple of years.